the trunk and the canopy. Here is a simple drawing of both of them in profile. We draw the trunk this way. Well, we don't know that it is conical, but basically tapered, so that the trunk has a diameter called D trunk at location X. X is the coordinate starting from the tip. All these beams you've been learning. The smart way to do the math is to start the longitudinal coordinate from the narrow end. And then the canopy is a body that's wider, and one that has another horizontal dimension called D of the canopy, which depends on its own X, its own level. Get it? And of course, as I said already, the tree is being pushed from the side by the wind. The simplest kind of wind is the one that I just drew. It is one that's uniform. And the force exerted by that wind on the canopy, because the wind sees the big, not the small. The wind sees the animal, not some bone inside the animal. So the wind drag per unit height, so that's the force per unit height, is F prime. And at this location called X, the F prime is equal to, well, it is the drag coefficient, and then this slice of height dx, the frontal view faced by the wind is dc dx, and then 1/2 rho v squared, where v is the speed of the wind, which is uniform. What does the wind do? In fact, let me do the following. I'll blow up this this portion of the drawing, and I will put it up here. Here is the trunk. The canopy would have been this way. The X starts here, and there's this F prime force, so that's the location X. F prime is pushing the canopy, but the force is taken by the trunk this way, F prime, and so on. And it is trying to turn the top of the tree clockwise. How? With the contribution from every single arrow of this type, an arrow that is located at altitude psi. So every little arrow contributes to the bending moment felt by this top of the trunk. And that moment depends on location X, meaning the moment is felt in this cross section, which is at location x, and it is the integral from 0 to x of f prime at location x times the arm of that moment, which is x minus psi. See, the arm of this particular f prime is the arm of this f prime is this chunk, which is x minus psi, and then dig psi. So the bending moment can be evaluated with this integral, and in which f prime is given by this expression, in which dc is an unknown function of x. But again, because we're not born yesterday, we just figured out that assuming power laws is a useful move, we assume that dc as a function of x is a function called a x to power n. And substitute it first in the f prime expression, and then into the bending moment, we obtain that the bending moment at altitude x, which is here in this chunk, meaning at the base of the top of the trunk, is in fact, this is, I'll write it this way, is equal to a constant a prime, and then x to n plus 2, and then n plus 1, and then n plus 2, where a prime is the shorthand for another constant, namely a, and then 1 over 2 rho v squared, and then cd. And this bending moment that tends to rotate the trunk clockwise is counteracted by another moment that's due to the stresses in this cross section, and remember so if the rotation is this way, then you'll have tensile stresses in the dorsal fiber and compressive in the ventral fiber. They vary linearly. We've done that sketch in the past, and this one is called SM at location X. The formula for that is the bending moment at location X divided by the area moment of inertia of the trunk, because that is the solid that's being bent here. And then here was the transversal dimension dt at location x divided by 2, where the area moment of inertia is pi over 64, and then dt to power 4. And you're with me? And now we invoke another idea from the past. If we're to make all these maximal stresses, which in principle depend on altitude x, to make them all equal to the maximum allowable stress, meaning we're making now the trunk of equal SMA along the height x. So if SM equals SMA, constant. So this becomes a constant. From the right-hand side, then m is a function of x divided by the trunk diameter to power 3 must be a constant. The bending moment goes as x to m plus 2. And that means that the trunk diameter, so this is the conclusion here, that the trunk diameter at location x must be a constant. I'll write it here, 32 a prime slash pi over maximum allowable stress, and then n plus 1, n plus 2 to power 1/3, and then x to power n plus 2 over 3. So we arrived at the, almost at the end of the road, which is that the lightest design for the tree that packs least carbon material is this one, shaped with that particular shape, which depends on n. N is the degree of freedom. The canopy itself depends on n. So you've got two things that depend on this degree of freedom: the canopy profile and the trunk profile. And the real punchline that made me proud when I was able to articulate it is the following. It's a very short table. If we assume that n equals 1, which means a cone, meaning the canopy is a cone, then the exponent indicated here for the trunk that exponent, I will write it, let's put it in a circle, is 1, which means that the trunk is a cone as well. This is the drawing that I made here at the start of this analysis. Now let's deviate from this easy guess, and let's assume that the canopy from a distance has a round top, and that's indicated by n equals 1/2 as a pick. So round top. So from a distance, the canopy looks like this. You've seen trees with this kind of outlook, the apple tree all the way to the, never mind, most trees look like this, okay? Except the biggest of them all. I'll show that to you in a second. The round top, then the exponent indicated by this double circle. We'll have that exponent would be x, meaning x to 5 divided by 6. And 5 divided by 6 is very close to 1. Interesting. If, on the other hand, the tree from a distance looks like a Christmas tree, meaning with a sharp tip, like a lightning rod, that would be 3 divided by 2 would be one example. Then the result you get for this factor is x to power 7 divided by 6, which is once again close to 1. So this entire, let's call it design from the point of view of natural behavior, teaches that the shape of the trunk is relatively insensitive to the shape of the crown. And so whereas all trunks are essentially conical, you know, narrower and narrower as you proceed to the top, the canopies that these trunks are supporting exhibit diversity. And that diversity does not come in conflict in any way with performance. And this performance is what we've been pursuing in this demonstration. And that is a structure that vehicles this water flow rate from the root upward the most per unit of volume, which was invoked in all these pieces of analysis, that volume being fixed. I get it? So in the beginning, there is the degree of freedom. And then one of the reflections of the presence of freedom in the evolution of the design is the presence of diversity. In this case, the diversity at the larger scale, which is the canopy. And the larger scale is the one that cannot be dismissed. It's obvious. It's a lot easier to see the canopy than to see the trunk that supports the canopy. All right, let me see what else I want to tell you. Oh yeah, so round top, sharp top. The tree with the sharpest top is the Eiffel Tower, which is all trunk and no canopy. And that is actually the secret to how the great engineer Gustave Eiffel designed his structure. He designed a structure that was like in what I put on the blackboard, where the canopy was absent, and but the trunk was taking all this pushing from the side without breaking, but also with the distribution of maximum allowable stresses through that truss-like structure that he had to design. Any of you have heard of Antoni Gaudí, the architect of the La Sagrada Familia in this cathedral in Barcelona? And what a guy that was. Gaudí was a disciple of Eiffel. Think about that. In other words, the real schools or the schoolmasters are few, and you see reverberations of the master spirit in the immediately next generation in this story represented by Antoni Gaudí. All right, I'm impressed that you've heard of Gaudí, and now you've heard once again about Eiffel. I told you Eiffel is the one with the skeleton of the Statue of Liberty. He did. That's a tree, the statue, and then the arm holding the flame is the equivalent, but smaller scale. So it's one Eiffel Tower holding a smaller Eiffel Tower. If you look at the structure of the Statue of Liberty naked. You should do that.